let's go ahead and start. Welcome, my friends, to a 388 review. This is Econometrics. If you are in the wrong class, you're welcome to stay, I guess. But I'm going to try as much as I can to do a comprehensive review of this class. It's a little bit difficult, and there's a lot of stuff that I won't cover. Most of the stuff that we already covered in the midterm 1 review, I'm not going to comprehensively recover. So like hypothesis testing, for example, is something that I'm not going to go into. You can go and watch the midterm 1 review if you want to review that, and similar things. But we will start from just where we started in the very beginning, which is with a question, right? Econometrics has a question, model, data, estimation strategy, inference. We communicate our findings to, and this is really how we build out our understanding of the world. Okay. If you remember, or if you were here during midterm 1, we discussed a situation with a girl named Zoey, who was a demon hunter and also happened to be a K-pop star. And she was wondering, does spending money on makeup help me kill more demons? She was convinced that it did. So if she was going to choose a model, she'd probably choose a model that says something like, my makeup spending, or the makeup spending for a demon hunter would be, some linear combination related to this X and this. Whoa, did I say makeup spending? I mean demons killed. Why is it going to be demons killed? Okay, it's going to be some linear combination of makeup spending and then some unobserved error. And this is a model. Okay, and then she would choose some data from this model. And let's say she would choose a cross-sectional data, right? So she would have, you'd have a data set, which would be a bunch of individual, demon hunters, and then they would all have their own makeup spending, and you would run a regression on that. That would be some cross-sectional data set, okay? And then you would estimate that with like OLS, right? Here's my estimation strategy. I'm going to use OLS, and this is going to be subject to the Gauss-Markov assumptions, okay? And so he went over those assumptions. You have assumption A0, which is the existence of an inverse. Yes, very good, very good. You have A1, zero conditional mean. You have A2, which is very good, homoscedasticity. A3, which is perfect, yes. And under those assumptions, then OLS is blue, right? It's the best linear unbiased estimator. Okay, so she might choose to run, such a regression. But here's the thing: there's this, strong assumption that she's making here, which is that, estimated epsilon given x is 0, right? Exogenity A1, and that's actually most likely to be violated when people can self-select, right? And you'll have people that can self-select into how much they spend on makeup, and additionally how many demons they kill. So because there's selection, you might think that there is some omitted variable there, right? So you might perform a multiple regression under your conditional independence assumption, which is that, okay, if I include all these variables, then maybe I can get to the point where exogeneity holds, right? And so you run a multiple regression, which is your y equals x beta. Your beta hat is going to be, x transpose x inverse, x transpose y, right? This is still all review at this point for midterm 1, and you guys hopefully know how to define all of these matrices and vectors and variables and all of that, right? So we could do that to eliminate omitted variables bias, right? And we could write that all in matrix form and everything. We covered all of that in the previous review, but maybe Zoey decides, okay, I don't want cross-sectional data. That's lame. What I want is I'm just going to take myself. I'm going to take some time series data, right? And in my time series data, I'm going to have a little bit of a different model. Here's what my model is going to look like. It's going to be very similar, but instead we're going to do it just for Zoey. And for Zoey, her how many demons she kills in any given time period is going to be some linear combination of the makeup that she spends, or the amount she spends on makeup in that time period. And boom, just like that, we have a time series. Except the problem with time series is that it's subject to a lot of problems. Okay, it's still under the same Gauss-Markov assumptions, but one thing that you might think in time series is that the amount that she spends on makeup in 1 month might be correlated with what she spends on makeup in the next month, right? So she spends, a normal amount, like, $5,000 on makeup in month 1, and maybe she has some extra makeup, so that's a little bit correlated with, how much she spends on makeup in month 2, right? Maybe she's saving a little bit. So one way you could look at that is with a FDL, finite distributed lag model, where your YT is going to be, should I still use betas? How does he do this? He uses he's an alpha, doesn't he? So let's say you still have some intercept, but now you're going to have some initial makeup spend variable, right? So, but then, maybe it's also dependent on how much she spent on makeup last month. Maybe she even buys so much that it's dependent on how much she spent on makeup the month, and that's an X. The month before, right? And this can go on for forever and ever and ever. And then you can have, well, not forever, but you have delta Q, that's a Q there, and then XT minus Q. Okay, so that's what a finite distributed lag model looks like. Oh, sorry, you should always include your error term there. We'll call that U, because we're in time series land, and we call it U in time series land for some reason, and it's also, subject to time. So that's what an FDL looks like, okay? So that's one dynamic model that we have. There's a lot of pitfalls also that time series falls into. You could have trends, you could have seasonality, you could have dependent data. So if you're working with trends or seasonality, basically, it's pretty simple. For trends or seasonality, you just want to include time. Okay, that's the simplest way to do that. Yes, you can also regress your y on t and regress your x on t, and then regress the residuals from one of those on the residuals of the other one. That's called Frisch-Waugh. But that does the exact same thing as just including t in your regression. So that's how you would do trend. You can do that in terms of trends. Seasonality, you can include dummies, right, for each time period.
How important would you say it is to know the alternate way to trend rather than just say include t in the, Because if I'm always just gonna say include t. I'm never gonna say the other one.
Cool. How many of you guys have done a practice final? Oh, nice. Okay. How many of you guys have you done more than one? More than two? Sick. Okay. Did you see Frisch-Waugh on any of those? No. No. Let's go. Okay, well,
I guess you could have, because it was what can you do about this?
Yeah.
But if you just say include time.
But that would have also answered the question.
Yeah.
So there we go. Okay. What else? Something seasonality. So if we're talking about dependent data is pretty simple. You could have autoregressive dependent data, which is where some variable, let's call your variable x, it's actually dependent on itself, right? So it equals some function of x. Or you have moving average dependent data, where x is going to be a function of epsilon. So in one case, x is dependent on itself. That's why it's called autoregressive. And moving average, x is dependent on the error term. Okay, and you can have those persisting from time period to time period. So for autoregressive data, when it's dependent on itself, you could have weakly dependent or strongly dependent. It just has to do with your row in your equation. So if your x equals some what is it? Is it rho xt plus something something something? Is that right? I didn't write it down.
Yeah.
Is your row on X?
It's like t minus 1.
T minus 1, sorry about that. Yeah, so if your row is 1, it's not going to be more than 1. Because, as Dr. Franson says, the universe would explode with more than 1. Okay? So if it's 1, you have strongly dependent data. Which means, and if you have strongly dependent data, then OLS is going to be inconsistent. Okay? If it's less than 1, then you have weakly dependent data, and that's more acceptable. But if you have strongly dependent data, you can first difference in order to get rid of that. Okay, so first difference, your dependent data. And then moving average, when it's dependent on the error term, you're just going to have some weakly dependent data there. And for a moving average, the way to fix that is you can Nui West your standard errors. Okay? So use Nui West, pack robust standard errors to fix your moving average dependent data. Okay? It's dependent data, trend seasonality, yes.
So will you always use Nui West standard errors for any kind of dependent data?
That's specifically for moving average when X is dependent on the error term. Yeah.
So autoregressive, if it's strongly dependent, you do first differencing, and then for either, if it's moving average, you do Nui West. Do I have that right? Like, wait, I think I'm confused. Sorry, so I'm thinking in terms of so autoregressive. Can you just like run through the solutions like in 2 sentences?
Sorry. Oh yeah, sorry, I didn't write down the solution for autoregressive. But can you use Nui West for that as well?
I think you usually just use yt minus 1 is what it says in the regressive.
Oh, so either way, you first difference?
First difference for autoregressive, but you should use just Nui West for.
Whether it's weak or strong in autoregressive?
Good question.
Because first differencing is only for strongly dependent. You're right.
If it's to include like a yt minus 1 as a regressor.
Oh, okay. So that's it. Just put yt minus 1 in your. Okay.
On the right side.
Cool. Thank you. Thank you for that. Okay. Cool. Any more questions about that, or did that clear it up? Okay. Perfect. All right. So we talked about dependent data. We talked about trends. We talked about seasonality. And okay, so that's all we are going to talk about in terms of time series, right? So there's some issues with that. So maybe instead of time series, we're going to mix all of this. Not go with the dynamic models. Instead of going with a dynamic model, let's get like a panel, right? Let's get like a bunch of every demon hunter in the area. Right, we have them, and we have that like it's 3-dimensional. It's like a cross time, right? So it's like a 3-dimensional cross section. I'm envisioning that in my mind. I don't know if you guys are, but basically, so then for every individual at every time period, it's going to be some function, of the same thing, but it's going to be their makeup spend, right? The units they kill in the specific time period is going to be dependent on their makeup spend for that specific time period. So you're going to have this big thing. Are we back to epsilon now? I think we are. And so that's your, and epsilon IT, we usually split that up and we say, okay, let's say there's some part of that that's just related to the individuals, right? This is the characteristics of a specific individual. And then we have some part that's truly random, truly idiosyncratic for every individual and time period, right? And we can say like, yeah, for every individual and every time period, like there's probably a bunch of random shocks that go on. But this right here, to say that remember we're assuming exogeneity here. So if we're assuming the expected epsilon IT given x is 0, right? Then we're assuming that about both of these things. And this we can believe, but this is what in econometrics we call sussy. Okay? That's obviously, if we look at one individual like Zoey, of course that's not going to be random, right? Of course the expected her expected
Skill.
what am I saying? It's gonna be different, right? Her error term is gonna be different, systematically different than another individual, right? She's gonna spend more on makeup probably than someone else. That make sense? All right. So we're worried about this. So we want to fix the problem of the sussy alpha. Okay. So how do we fix the sussy alpha? There's two main ways. All right. There is the first differencing way, which we just talked about. Right. This is where we murder alpha. Okay. It's the mafia method. Remember this? Okay. So now we're gonna first difference. We're gonna take the difference in YIT is is related to the difference in XIT, right? So if I were to write all this out, I guess I could write all that out. The difference in YIT is going to be YIT minus YIT minus 1. Do you guys want me to write it out and prove to you the difference and everything? Okay, I'll just write the difference in YIT is going to be some function. The beta naught is going to get murdered, right? And then you're going to have beta 1 times the difference in XIT, all right? And then alpha is going to get murdered. And you're still going to have nu, okay, plus nu IT, okay? So that is what's going to happen with your first differencing equation right there. Yes?
Is there delta on the error term? Or just...
On the error term, no, there shouldn't be.
Because, well, it's...
Are you taking the difference of it?
Is it? Oh, is it?
Because it has a t on it, so wouldn't it... Well, I mean, that's not observed anyways, right? So...
Yeah, you know what? I can do that. Yes, okay, so that's your first differencing equation right there. Yeah, yep, exactly. And then another way to solve that is fixed effects, where we include the alpha, okay? So instead of killing the sussy alpha, we include it. And this is called the Church of Jesus Christ of Latter-day Saints method. Right? I'm like, seemed like in class that Dr. Franson was like, well, if we have a new prophet, I guess we're going back to the old way of doing things. What are you talking about? So, fixed effects, right? You have your YIT, right? It's going to be your beta naught plus your beta 1 XIT, right? Plus, okay, so then you're going to have like basically a bunch of dummies. You're going to write that like that. You have a set. You have a set of your alpha i's, right? So basically, you're gonna, if you're comparing everything to alpha 1, because you're going to leave a dummy out, you're going to have alpha 2. Well, okay, it's going to be like if this is like. This is hard to explain. Okay, basically, if I am individual I, then alpha I is going to show up here. So you can leave out individual 1, but if I'm individual 2, there's going to be an alpha 2 here. If I'm individual 3, there's going to be an alpha 3 here, and so on and so forth. Does that make sense? Yes?
Is there a coefficient on those as well? And is it like a different letter?
Yeah, there should be a coefficient on those, shouldn't there? So, well, the coefficient essentially is like, if I were to write like alpha I times like 3i is
alpha I is the coefficient.
Is something that I've seen it written as. So your alpha I is your coefficient, and then di
is for the dummy.
Is like, you know, is it if it's 1 if you are the individual, and 0 otherwise. Okay, and then finally you get your nu over here. Okay, so the idea behind fixed effects is that you are including all of these things in your regression. So you can see your alpha i's. Yes?
Sorry, just to clarify that. So if we have a set of like 5 people in this panel data set, would we have 4, like just say like four of their names would be the dummies, for an example?
Yes. So you'd have a dummy if you're like if you 5, 1, 2, 3, 4, 5. If you 5 are in the data set, then I'd have a dummy. If you're Spencer, well, or I could leave you out, right? Maybe you could be the one left out. And then everyone would be compared to you, and I have a dummy for each of you guys.
So then that alpha is just your beta 0 essentially. Is that right?
Well, yeah, this would be if,
The expected value of the person that left out.
yeah, because if you're Spencer, all of this is going to be 0. So then you're going to have your constant right there. So everyone is going to be compared to, like the alpha I, your alpha I is going to be how different you are from Spencer.
Into Spencer's alpha.
That makes sense? Yeah. Cool. We all good on that? Handle data stuff? Okay, so we know pooled OLS is bad because of alpha. We can use fixed effects, which is also called the within.
What does pooled mean? Is it just
Oh, it's just
referring
because
to
it's panel.
phenomenon where you have the alpha?
Because it's panel data, we call it OLS pooled OLS. That's
Just treating it like normal, like a cross-sectional. Right?
yeah, it's just like OLS. Like if we were to run OLS on this, it'd be bad. Like our exogenaity would be broken. So that's all that says.
So is pooled OLS biased? Or, because I think that was one of the questions.
Or is it just
Yeah,
inefficient?
so exogenaity is broken, and the result of that is that OLS is biased. Yeah. Okay, perfect. And then we can use, or we can use first differences to solve the problem of covariance between alpha and x. Okay, a special case is difference in differences. All right, so let's do difference in differences. So these are a little graph for you guys. And let's say we observe some treatment, right? And this is a very simple, like 2-period. We have like a before-after type thing going on. So we'll have a non-treated group. We'll have a treated group. Okay. Let's say our treatment is, I don't know, we like give you 10 grand of free makeup, right? Okay. As a little randomized control trial. All right, and in your non-treated group, we have, this going on for your observations for demons killed, and down here in your treated group, we have maybe that's going on, right? So you're observing this difference in differences between your treated and non-treated group. And the difference in differences is going to have your YIT, and it's going to be some function of, well, you're going to have your beta naught. You're going to have beta 1 treated. That's are you the treated group or are you not, right? For the individual, you're going to have beta 1 or beta 2, I guess, if you are after on time t. So are we before or are we after in terms of time? Okay, and then you're going to have some. I'm going to run into these. You're going to have some coefficient on treated times after, and this is only going to be 1 if you are the treated group and you are after, plus some error. Do we still call that nu? I guess we call it epsilon. You can call it whatever you want. I don't care. Okay, so that is that was the wrong one. Okay, perfect. So that's a basic difference in differences with just like 2 time periods and 2 groups, right? Which is on a lot of these practice tests, like this Miami-Jacksonville one right here.
So Stephen, is the coefficient that we care about the delta in that case most of the time?
Yeah.
Or is the delta just thrown in to kind of control?
Let's see, your coefficient, because you want the, I haven't thought about difference in differences in a while.
So,
It should be because it's what happens after and to the treated,
yeah.
right?
The delta, yeah, I think the delta is the one we're looking for.
Yeah,
And
it's-
that's when you solve for difference in differences.
Yeah.
Subtraction, et cetera.
Perfect. I like it. I like it. Okay.
Wait, I have a question. How do I interpret an interaction term? Like that coefficient, like what does that mean in English?
So this, I mean, for a difference in differences, like this is solely so that you can have this be 1 when you are a treated group after,
Okay.
That's the purpose of the delta.
Okay.
In other cases, like in other regressions, if you're doing an interaction term,
Like if I was looking at marginal effects, for example, like what does it mean?
wait, sorry, one second.
Delta is the
Like in front of the building.
because it's what's happening after you're treated. Modeling essentially.
Oh, we can go out. He's
got us hostage.
in front of the building.
No.
Yeah. It's like the amount of
I might need one of you guys to leave the premises for a sec and retrieve something for me.
Pretty saucy.
Steven has the weed.
Part of the test.
Yeah, can I get an extra credit point for that?
But for
you
other
grading?
what?
Are you grading them?
Yes.
Okay.
What else would you like?
Other questions? Okay.
I was just wondering how many.
Okay, sorry, just clarification on the variables here. We have TR and AF. TR is treatment and then after, but which treatment or which treatment after? Does it?
Would you like an example of this?
Well, is it just an abbreviation? I'm just trying to, because I know that there are 4 parts to it. It's like before minus after the first one minus before and after the second. Or maybe it was like before minus before and after minus after. But I just don't remember the exact.
It's just
Let's look at an example. Maybe we should draw an example of this. So, there's one on all. What is this? Oh, winter 2025. Let's look at that. Do you want the projector, or do you want to crank your heads back to the TV?
And what's in the parentheses? My eyesight's terrible. TR.
Treated times after.
Okay.
Yeah. That might be hard to read. I'll give you the projector. We'll look at an example so we can really understand this.
That's all we have to do.
Oh.
Someone interacting here is very weird.
Oh, yeah.
Steven, just a quick question about like the test. He said that he would apply a curve. Do you know how this curve is applied? If it's like a curve on the test, on the class, just like.
The curve would be at the end of the class.
Okay.
It wouldn't be on the test itself.
Gotcha.
I don't think.
So like the grade that we have in Learning Suite or whatever, we can just like disregard like. Right, but like. Sorry, I'm sorry. I digress.
In examining your panel data, okay, you focused on a particular episode from April to October. During this time, 100,000 Cubans settled in Miami. Jacksonville had no appreciable change in immigration. Here's a subset of your panel data for these 2 cities. You got Miami 79, you got Miami 80, and Miami had the influx, and then you got Jacksonville 79 and Jackson 80. Okay, what's the assumption underlying diff and diff? You guys know what that's called?
Parallel trends.
Parallel trends. You're assuming that what happened in Jacksonville would have happened in Miami if Miami had not had the immigration influx. So here's like essentially how diff and diff works, right? You see the change in Jacksonville. It's 7.5 to 7.3, okay? So the change was negative 0.2. Agreed? You all agree on that one? Okay. Then the change in Miami, 8.3 to 8. So it was negative 0.3. Ooh. Okay. So if Jacksonville was negative 0.2, and that would have happened in Miami, but instead Miami was negative 0.3, then what's your what's the effect of immigration?
0.1.
Negative 0.1, right?
Yeah.
Negative 0.1?
Yeah, that, I guess.
Yes. Like from the board. Oh, up there. Okay. Gotcha.
Man.
All right. Okay, we'll send someone.
Yeah,
They
don't get
ordered roses for us today.
Cosmo's coming.
Cosmos
Let's go on a run real quick. Lexi?
Like up there or over there?
He's up by the Westview building.
Like go up all the stairs?
Yeah.
By the Westview building?
And what does she
Well, he's
look?
not at the Westview building. He's up like.
Oh, it's
holding
top of the tent.
Dr. Franklin?
Okay.
No idea.
So, does that make sense for diff and diff? Does that clear it up?
You guys, like,
I mean, that's essentially how you do a diff and diff problem. What estimation strategy you use diff and diff, right? What's the effect of a large influx in units? Negative 0.1. Did I get negative 0.1? I did. Wow. And I got a check mark. So you know it's right. Okay, diff and diff, are we solid on it?
Yeah.
Okay. Perfect. Okay.
So our key assumption is parallel lines.
It's about knowing the models and when to use them and their assumptions.
A generalized form of diff and diff would be like if you had multiple, you know, this is just like a binary case, right? You have 2 time periods, you have 2 places. You could do beta naught plus, and then you could have a set of alphas and a set of gammas, and then here's, you know, some, I will write these as sets now actually. And so essentially like a generalized diff and diff would be like you would have a set of dummies of alphas, like you have just one dummy here for treated, right? But you would have a bunch of those if you had like a bunch of different groups. And then same thing for the gammas. Instead of just one after, you would have a bunch of dummies for like which time period you're in. And this S is just meaning here like it's going to be 1 if you are the treated group in the treated time period. Yeah. Okay, so that's a generalized diff and diff. Yes?
wait, so, sorry. I feel like I've never seen that in my life until right now.
No?
Building.
Yes. Okay. Sorry. Go ahead.
So is that just like, that's not fixed effects version of diff and diff, is it? Or like, what is that?
So diff and diff is a specialized case of fixed effects.
Oh, okay, got it.
So that's, you want to make sure I'm saying that right.
Okay, so that's just the generalized version.
Yeah. Yep, exactly. Okay, so any other questions about diff and diff or general panel data? Yes.
Could you write the generalized equation a bit bigger? It's just kind of hard to see from here.
Sorry about that.
The subscripts.
I don't exactly know my handwriting. Okay. So that's an IT. Probably got a beta naught. Or I guess you'd have some set of like I's here. Some set of please. Got big enough?
Oh, that's big.
Is that good?
Could be more props.
Zoom out your eyes.
Thank you.
Hey. Oh my gosh. Lexi brought pizza.
No.
Thank you, Lexi.
You're just gonna eat it all. There's probably
This
dinner.
Was he friend?
I don't know, he had put Jackson.
All right, if you guys would like some pizza, please up here.
No, I had to.
Should we?
Yeah, thank you, Steven. Yeah.
like and subscribe.
You are the subscriber today.
As I was just hungry.
I was late.
I don't have napkins or plates.
Should we just pass them out? Yeah, we should.
Yeah, just pass
Yeah,
it.
Pass the box.
We'll go from the top.
Any more questions about that? Before we end this. Okay.
Right.
Okay.
Wait, what are the curly brackets?
That's just like a placeholder for like you're going to include a set of dummies for your alphas. It's like treated, but instead of just one dummy for treated, you have a bunch of those for every individual. And same for after. that make sense?
There was an error term at the end, right?
Yes, there is an error term. Okay.
Back to the mission.
All right, then you guys talked about instrumental variables, right? For IVs, they depend on two assumptions. What's assumption one?
Relevance.
Well, I would call that two, but okay, whatever. You have exogeneity and you have relevance, right? Exogeneity says that well, I'll write it like this. It says that the covariance between your instrument and your error term is 0. Okay? Relevance says that the covariance between your instrument and what you're instrumenting for is not 0. Otherwise, it will not be relevant, right? Pretty simple stuff. Okay? You need exogeneity and relevance to hold for your IVs. When you're testing your IVs, which you guys talked about testing a little bit, you would use, like let's say you have multiple instruments for that one X, right? You might want multiple instruments because you have, well, if you have more than one X, yeah, obviously you want multiple instruments. But also, it can give you more precision in your IV estimates. And it also gives you the ability to test your exclusion. Okay? So you can do that as well. There was only one, like to my knowledge, the only like proof or derivation that Dr. Franson has done since the last midterm is the consistency of, is like IV consistency. And that's like a pretty straightforward proof. You start with your, all right, you have your covariance of Z and Y over your covariance of Z and X. Yes? That's your beta hat 1 IV.
Which one is the covariance of what?
Z and Y. Okay? You take that, you plug, those are samples, okay? And you converge to infinity and you get, the actual covariance over the actual covariance. Okay? After you do that, you plug in for Y and you're gonna get beta 1. And boom, you have proved, you're gonna use the assumption of exogeneity in there.
Should we point that out?
Yeah, would you be willing to work that out?
Yeah.
Or should we point out when the assumption applies?
Guys, I believe you can do this, okay? Covariance of Z and Y, or the covariance of Z and X, okay? Plugging for your Y, you get the covariance of Z and beta naught plus beta 1 X plus epsilon, okay, over covariance of Z and X equals, distribute your covariance, the beta naught, that's just a 0, so you get the covariance of, you get beta 1 covariance of Z and X plus covariance of Z and epsilon over covariance of Z and X. Boom. Exclusion restriction, right? We assume that's 0. That's by assumption. Ta-da, beta 1. Cool. Nice.
Wait, sorry, so the EX, that stands for exclusion? The IVs right next to that?
Yeah, so exogeneity and exclusions,
Okay,
either of those interchangeably in this class.
Should we be afraid that the proofs from the first half of the class will be resurrected on this test? Because I don't remember them at all.
I personally did not see those on the practice exams. Anyone that did practice exams, did you see old proofs?
There was like an omit variables bias one, and there was the 2019 had like the variance matrix one.
Oh.
Yeah.
I don't think it was the proof. I think there was like the OLS proof.
Oh yeah.
Like deriving.
Yeah.
Yeah, derived
There was
beta
one of the
0 and
matrix.
beta 1.
Wait, like bivariate?
Yeah.
Yeah.
Oh yeah.
Really? That was on one of the practice exams?
Yeah, from like almost a decade ago though.
Okay, so in theory, you should know everything.
Could you talk real quick about measurement error and attenuation bias?
I was afraid someone would ask that.
Go to the ladder.
Isn't there also simultaneity or causality?
Yeah, I mean, those are all like highly related in their proofs.
Very similar.
So
I mean, yeah, that's true. That's true.
yeah, so I think you did one of those on one of the problem sets. You've definitely done reverse causality.
Yeah.
But you did a measurement error one on one of your problem sets, yeah?
I think so.
Yeah.
So that would be. Want me to find out what problem set that was?
So I'll go back. I'll find it.
Okay. That's yeah, it's in the solutions. But it's very similar to reverse causality. And he'll give you the assumptions just like he did on the problem set. And I mean, just like these are, if you can do one of these, you can do pretty much all of them. Reverse causality, the only thing you need to be aware of is that there's two sides to the equation. And at one point, you got to solve by using both sides of the equation. But other than that, these are all like very similar derivations. You're just gonna like plug and chug. Okay. What else do I want to say about IPs? I mean, you know that like in the matrix case, that your beta hat is going to be G transpose X inverse G transpose Y. I guess that's when you're just identified. Right, you're going to have Z transpose X inverse Z transpose Y. That's the matrix version of that.
There was a proof for that one too, right?
Yes, I was going to ask, do we need to know that proof? Because I don't think you showed it in class, but it is on the sheet of proofs.
It is, but I thought he specifically.
I think he said it's not.
No, he specifically said we don't need to know.
I do remember that. Okay. And when you are over-identified, then you can use your two-stage least squares, right? So the process is you regress your x on your z, and you regress your, and then you get your x hats, and then you regress your y on x hat, okay? And you're going to use x hat as an instrument in your just identified formula. I don't know if that was on any of the practice tests. I don't remember seeing that in the practice.
It is.
It is? Okay. Well, then you should know that.
Can you write that out?
X on Z.
There's a stage, there's two. There's least squared.
I wonder if that was on here.
Yeah, I don't know.
What?
Commands are on the side.
These two square stages.
No, this is just like how we would do it. How did I write this?
You have an hour to
Aha.
You have an hour to clean it.
Write a two-paragraph memo.
Here is a zips to county crosswalk.
Oh, the crosswalk.
function.
Yeah, only help function. No,
I'll put it more confused.
Predict x hat regress y on x hat. Okay? So if you know how to do this, okay? Maybe this is why I'm writing it this way. All right. AKA, right? I'm gonna write this in the squiggly way because I think we use this as squigglies, maybe. I don't know. Okay, so you're gonna regress. Okay, you're gonna regress your x on your z. So you're gonna use your x hat. Okay. Z transpose z inverse z transpose x. Now, hat equals x hat transpose x hat inverse x hat transpose y. So, y hat equals x hat beta hat. And that's how I would write that. Questions? Yes?
So is this just like another derivation that we do need to know on the test besides the instrumental variables?
I am looking at this final, and this was a specific question. Give a formula or describe in detail how to obtain the estimate in two-stage least squares.
Okay. And then the describe in detail would be everything that you did on the right.
Yeah, yeah. I don't know if this would be though. So,
I mean,
probably.
I write out the whole explanation.
This was the whole. That's all I gave.
I thought you said it wasn't enough.
No, this. Okay. Yeah, this right here. Although you could try it. It's not something that I tried. So.
There's a question I think about like potential downsides of measuring variables, as well as using one instrument for multiple regressors.
You can't do that.
You can't do that?
That's not a thing.
Okay. Using what?
One instrument for multiple regressors. Yeah, it has to be at least just identified. Under-identified, that's not. Okay, all right. We talked about IVs. The only other stuff on IVs are a Hausman test. So yeah, you do have a Hausman test. And for a Hausman, I'm going to write this in similar terms. For a Hausman test, you are going to regress your y on your z's. Okay. You're going to regress y on your trusted z's. Okay. And then you're going to compare them in a two-tailed hypothesis test. Okay, your H null in this test is going to be that your beta hat from OLS, or what you're comparing to, is your minus your beta hat IV equals 0. You're gonna your null is that they're the same, and your alternative hypothesis is that they are not the same. Okay, so that is how a Hausman test would work. Should you theoretically be asked to do one? Sorry.
So the first beta hat one in your null, is that from OLS or from, like, because we were going over a practice problem earlier, and like the key says it's like that comes from a subset, but
Yeah.
then is that the same thing as OLS?
I think usually you are comparing it to OLS, but it doesn't. There's not a reason it has to be. Because I think a Hausman test can be used for multiple different things, but I think that's the only way we've talked about that in this class, to my knowledge. So you regress it on a subset of your z's, or sorry, you regress it on all your z's. You regress it on a trusted subset of your z's.
Is that restricted?
Then you compare them.
Is that what it's called?
So aren't they all IVs? It's just that one is all of them, and then the other
The other one's the
subset?
trusted, yeah.
Yes. Okay, is that... See, you can use a Hausman to compare to OLS, but maybe that's what he talked about, is comparing it to a subset of your IVs. So you're basically saying, yeah, if all of them are IVs, basically you're doing all of your IVs, and then you're doing the ones that you're like, okay, these ones are the good ones, right? And then you're saying, okay, then, like, are these different, right? Like, is the beta hat I get from one different from the beta hat I get from the other?
How would you find the t statistic on that?
So in this problem, he gave you numbers, right? So he said for problem 21, we should pull up this Hausman Test problem. So he's just going through, you get some more instrumental variables. He asked, what's the name of the IV estimation procedure used? It's two-stage least squares. Give a formula for how to describe it. We just did that. Suppose your estimate from beta 1 were negative 0.7 with a standard error of 0.4. Suppose the standard error from your question to 14, that's kind of all the way back here. But in question 14, this might be a good one also, actually, just to show you. What's your bivariate IV estimate for the effect of immigration on local log GDP per capita? Well, it's the covariance of Z and Y, it's the covariance of Z and X, right? Boom, right there. Okay, so that's going to be negative 0.1 over 0.2 is, I don't trust myself with math right now. Negative 1/2. So that's what you got in question 14. So down here it says, okay, so suppose the standard error from your answer to question 14 were 0.5. Perform a Hausman test of the validity of your instruments. And I don't have really any bold space left. But here is an example of the t-stat. So we have negative 0.5 minus negative 0.7 minus 0 over the root of 0.5 squared plus negative 0.7 squared. Why does it say negative 0.5? Should that be 0.5? That should be 0.5.
That's a standard error and a beta value. I think we're supposed to use the beta from the previous problem there.
Well, I think in the denominator, it's 0.4, not 0.7.
Yeah.
Wait, this one?
Yeah.
It's 0.4.
Yeah, you throw 0.7 in the numerator and denominator.
Yeah, see, I did this question wrong. Squared. Okay, let's look at this and make sure it's right. Suppose your estimate for beta 1 was negative 0.7 with the standard, there's the negative 0.7, with a standard error of 0.4. Suppose the answer from your question 14, which we got negative 1/2. Oh, that's where I was a negative. Oh, okay. Okay, had a standard error of 0.5. Okay, so you're basically doing the difference of those, right? Which your null is at it's 0, right? You're taking your observed difference minus your theoretical difference, right, and your null, and you're putting it over the standard error of that difference. Which in this case, the variance of that difference, since they don't covary, is just going to be 0. So it's easy to get out. So
then would you simplify that? Because Dr. Branson told us that we should get easy numbers to work with, but then the numerator there, the denominator, is the square root of 0.41.
Let's see. Negative 0.5 plus 0.7 is 0.2, all right? And then 0.25 plus 0.16 is 0.36. Yes? So 0.2 over.
I think it's 0.41.
Did I not do that right?
16 plus 25.
0.25 plus 0.16. Oh, you're right. 0.3, 0.41, huh? Like that? Yeah, you're right. But it's like 0.4. us either.
I think in the notes, his formula is, because it's like the standard error of the difference. So when you simplify it down, it ends up being like the variance of one of the beta 1s minus the variance of the other beta 1. So then do you like have to square those standard errors and then take the difference of them?
Yeah, it is.
Oh, we just said that.
Subtract, right?
I don't know if it really helps the numbers, but I didn't square them.
Well, it does, because we get 0.09.
Yeah, let's just all get this wrong except for me.
Wait, Lexi.
Like, did you have it?
No, but I did the practice test and then chat did it. But it like got like 0.03 for the bottom.
It's, for me, it's showing that you subtract the standard errors.
Yeah.
And when you subtract it, you get point.
It's true.
0.09, which.
Yeah, because standard error by itself is literally already this.
Oh, okay.
Okay.
Subtract it here.
Okay, guys, we got it.
Yeah!
Sorry.
I think I might just do perks.
It's minus. It's minus. Yeah?
You just haven't passed it.
Seth, you want to? Yeah.
Share the love.
Yeah.
I need some comfort food.
Some stay right.
I've had pizza 4 days in a row.
More people wanted this? Or?
I haven't paid for it. Just if I keep going.
I did.
Do you know another?
As well, you like a king before I end up like a peasant tomorrow.
You want some? I'm good. You good? Oh, just pizza.
It's like the Last Supper.
Lexi, what did you get?
Take one. Here. Thank you.
Okay. Perfect. Okay. Trying this again. It's minus. Here's your variance. It's minus. I'll do it because that's the whole thing that the dude found out. I remember him saying that in class.
Yeah, it's like the thing that's like shouldn't make sense, but it does.
Yes.
Right?
Yes. The difference. The variance is the difference of the variances. I do remember him saying that. Okay.
Yeah.
So because of that, you get 0.25 minus 0.16, 0.09. Square root that, 2/3. We got it, guys.
I have a question on interpretation of the test. So if we reject it, if we reject, then our instruments are not valid.
Correct. Well, if you reject, there's a substantial difference between your subset of IVs and all of your IVs. Which, something's going on there, probably with the consistency of your subsets.
Does that tell us that it's in the one with all of them, or the subset, or is it kind of like not clear about it?
Well, it's your trusted subset. So you're assuming your trusted subset is valid when you run this. So it's saying that in all of them, you have some IVs that are invalid. If you fail to reject the test, it means that your instruments might be valid. Hence, fail to reject and not accept. Okay. Good. Nice. Okay, that's a Hausman test, and then you also talked about the Omnibus test, which I don't think was on any of the practices notes.
But you could have used it. I got
What?
15 on this list.
Well, in case you want to know how an Omnibus test works, you would run 2SLS with all your Z's, right? Run 1. 2SLS, all Z's. Okay? Then you're going to compute your residuals. Then you're going to regress your U hat on your Z's. Yeah, and then it's like an F test, and like your NR squared is chi-distributed. I think it's unlikely he's going to ask you to do that.
Will we have to worry about F tests?
I don't remember seeing one on any of the practice exams.
F and hope.
It is, everything's fair game.
Everything is fair game.
But some things are a lot more likely.
They'll probably give us the F.
How about Omnibus study it?
It's not as intuitive just to calculate that, but
Wait, Trent, is that?
Yeah, I mean, he didn't even talk to you about like what a valid
The residuals.
F test would look like.
so if we fail to reject, is it the same?
Of an omnibus test? An omnibus test is for what's
It's to see if the instruments are valid.
oh, it's to test validity.
It's like reverse causality or something. Which is a form of homogeneity.
I think it's for the
This is on the study guide that the Omnibus test allows you to test the assumptions of instruments.
Yeah, and honestly, on all the practice exams, that's really what it says. So, like the only question I've seen has looked like this. Reasons to obtain additional instrumental variables include. This doesn't even mention an omnibus test, but the answers are E and F. Right.
There was like, on one of them, there was like, give an example of one of the tests you could use and explain how to do it. So like, if you learned both and forget Hausman, I guess you could use Omnibus on a question like that.
Valid.
So going back to the Hausman, are we gonna have to specify like all the ingredients that T is distributed normally and that alpha equals 0.05?
It probably wouldn't hurt. Yeah, he didn't specifically, on this question, I don't see him specifically writing like all the ingredients. So on my test, I gave all the ingredients, and then I said, it should be bonus points because we weren't asked for all the ingredients. So.
I agree with that logic. I agree with bonus points.
No, I didn't get, I got less than bonus points. Because I did my Hausman test. Okay, so that's, all right, we talked about IVs, we talked about tests. Oh yes, Probit and Logit, right. The last things.
We spent a day on this. Yeah. We just spent a whole lot of time discussing what makes it IV.
And those aren't, like, right?
This one's kind of.
What's Probit? It's the,
Like two variants are gonna be split between
Standard normal CDF.
right? That's Probit.
and another sixth.
Where that is the standard normal CDF. You should probably say that. What's Logit? The way that he gives it in his notes, these are like G of W, right? What is G of W? The W here is whatever's in your ring function. So the way he gives it in his notes would be E of W over 1 plus E of W. It's a totally fine way to write that. Right? It's just the log of your probability over 1 minus your probability. So this is how he defines it in the lecture notes. And so that's how I would define it. That's Probit and Logit. And so again, like on this test, right? Oh, you guys can't see this again. It's rough. But at the very end of this test, it says, to estimate beta 1 in this model, rather than finding a line that minimizes the sum of squared distances, we find the coefficients that maximize the likelihood of the sample. Give the likelihood function that MLE maximizes, okay? So your likelihood function, you look like, and take the arguments, beta naught and beta 1, to maximize the product, y equals 1 to n, of your g's, and here's your beta knob plus beta 1, x 1 it, right? So that's, what your, whatever function you put in your link function is going to be there, yit, to the yit, times 1 minus g beta naught plus beta 1 x1 it to 1 minus yit. Okay, that would be a likelihood function. And then the last question.
And the one that uses, we'd be okay to write the one that uses summation? Because he did like 2 forms.
You get, when you take the log of your likelihood function, because your likelihood function is going to be the product of all of these. This is just a way of saying, like, you have, for like a bunch of these guys, you have a whole bunch of products, right? So that's what this is, the product from I equals 1 to n. So when you take the log of that likelihood function, that's when those products return into sums. So that's why you end up with a summation sign.
And we could write the log function if it asks for...
If he asks for the likelihood function, I would give the likelihood function. If he asks for log likelihood, I would give log likelihood, which is just the log of that. And then the last question says, define mathematically and derive the marginal effect, right? So if you were to take the derivative of g with respect to x, right, you would get g prime times beta 1. That's what you get.
Do we need to actually show our work for that derivation, or can we just memorize that?
I didn't, and I got it right. There we go. So that's the extent of what I imagine he would ask you about Probit and Logit. There are those couple questions at the end of the exam. And so in terms of content, I think that about covers it. So what time we got? 5:16. So we could, if you guys have specific questions about practice exams that you want to go through, or just general questions about the class, content, that we covered before I came in.
You, was it AR and
Really average?
Yeah.
And how, because he said draw a picture, yeah.
Oh, pictures?
Said draw a picture of
He
what?
know how to draw pictures for both those.
Oh, okay.
Is it just like
You could probably figure that out.
drawing a picture of like a trend?
I have it in my notes, but
An autoregressive might look like what? Xt equals xt minus 1 plus some.
no, I'm not the only one.
Something else.
What was that? Do you remember?
I didn't put the date on it, but it's time series. Are you looking for pictures?
Say absolutely.
We're gonna do it, yeah.
Yeah.
That's like essentially the.
Your notes are good for me.
They are. Otherwise, I just get lost. I like to really get my money.
Autoregressive.
Notebook every 5 classes. Moving average just goes and then hits 0. It's crazy.
Oh yeah. Sorry, there should be a row here probably. There should probably be.
The last of the test is a lot of conceptual. I'm chilling, but if it's any
Okay, so if you have an autoregressive process, then you're dependent on from before. I haven't drawn pictures of these before. I know that you have.
Steven, if you want.
Oh, you have pictures? Oh my gosh. Thank you.
It's like
Oh, man. Okay. Okay. So So let's actually write this like this. Okay, so moving average, he said, he used P. So P ET minus 1 plus P ET minus 2, it can go as long as you want. I guess I'll write it in the general form. So P1, P2, make these actual E's, T minus 2, P plus ET. Okay, so basically this is dependent on the path. So if you have a moving average, and let's say we're just doing 2. Okay, we're doing a moving average of order 2. Okay, so here's a little graph. This is a moving average of order 2. Okay, so up here, like we're gonna start. Here's time period 0, 1, 2, 3, 4. Okay, so in this case, your error terms are going to persist over time in your X, right? So we're going to start up at like the full effect right there, right? And then we're going to go down in time period 1. We're going to go down, and we would end up here. Correct me if I'm wrong. At P1. Correct, because xt would be et minus 1, we would end up at P1. Yeah, that's what this is saying. Yes? Sure. And then, on period 2, we would go down again. Here we would end up at P2. All right? That would, I mean, in this model, it can continue to persist for however, like whatever the order of your moving average is. But if you just have a moving average of order 2, then you would immediately, in time period 3, go down to 0, right? And now, you wouldn't have that error term persisting anymore. Okay? So this is just like, it's a graph of like showing the effect of your error term persisting in your X variable. Yes?
And then the sum of all of those is called the long run propensity, right? It's like P1 plus P2. All the way.
Thanks for finite distributed.
Yeah, I think you're thinking of FDL. So we call it that for FDL, but I don't know if we call it that for dependent data.
And wasn't there something about like comparing, like it's better to use one model when you have like limited number of time periods, and then like I think it was like at 2, they're basically the same, and then for like longer ones, it's better to use the other
That
one.
was fixed effects.
Yeah, that's fixed effects versus first differences. So fixed effects is preferred, but over just one time period, fixed effects and first differences give you the same result. Because fixed effects is the same, like fixed effects gives you the same result as if you subtracted off the differences from your mean, or the deviations from the mean, I guess I should say. And if you're subtracting out the deviations from the mean, but you just have one time period, it's going to give you the same result as if you're first differencing. So that's.
Sorry, could you write down just a summary of what you just said? Like when, like if t equals.
So that's right. It's been. I'll start with first differences. I think that's the first one we talked about. So we had delta y it is going to be delta x it plus delta mu it. Yeah, that's first differences. Okay, and then fixed effects we wrote down as y it is going to equal beta naught plus beta 1 x it plus plus you had a bunch of you included your alphas in there, right? So you had your set of dummies for your alphas, and then you had your error term in there as well, right? Am I including everything in there?
It was a gamma. I don't remember. You're probably good.
The gamma was in diff and diff.
Okay.
In the generalized diff and diff, that's what the gamma was. Okay, so fixed effects, like you showed in the homework, gives you the same result as if instead of these like delta y its, you were doing like you're doing something like this, where y squiggle is like y minus y bar, right? So when you're doing your deviations from the mean, that's what you showed in your homework, that gives you the same result as fixed effects. Those are fundamentally the same thing. And if you're doing just one time period, then this, it gives you the same thing as first differencing. Does that make sense?
So the y squiggle, that is for fixed first difference.
No, this is for fixed effects.
And then once it's more than one.
Then they're different.
And which ones, is there one that's better to use?
Fixed effects is preferred because it has a lower standard error. Yeah. Yep. Okay. And to try and answer the autoregressive question, you go to xt. Row xt minus 1 plus. Just add a bunch of those, and then you have some, some shock at the end. Okay. So for a autoregressive process, let's just look at. Well, I'll leave this here. Okay. 0, 1, 2, 3, 4. For an autoregressive process, let's do order 1. So we just have the row xt minus 1 here. Then, again, we're going to start at 1 up here, and then we'll go down to row, I should say row 1. Row 1, and then, okay, yes. And then, in time period 2, remember it's autoregressive, right? So this whole thing is subsumed in xt, like every single period. So unlike a moving average, what's going to happen is that this is going to be row 1 squared, right? And then down here, you're going to have row 1 cubed, and that's going to like keep going on until you hit 0. And that's why if your row is 1, then it's not going to dissipate, because no matter how much you square or cube that thing, or take it to the n power, it's not going to go to 0. Yeah?
Yes. Sorry, why would you use, which one would you be more inclined to use then? Or is it just entirely based on the behavior of
These aren't things that you use. These are problems with your data.
Oh,
These are examples of dependent data. So your x might be autoregressive, right? It might be correlated with itself it might be dependent on itself from multiple time periods in the past. Or maybe it's not dependent specifically on itself, but it's dependent on the error term for multiple time periods in the past. So that's the difference between moving average and autoregressive.
So strongly dependent would mean that it never reaches 0, right?
Yep, strongly dependent would be like that.
And then everything else other than that is weakly.
Yeah, this is weakly dependent. Yeah. Okay. Any other questions? Thank you, Trent. Okay. Do you guys want to end, or do you want to go over a practice exam? Do you want to go over a practice exam? Raise your hand. And I'll frankly sure. I see one hand.
I feel like everyone else has already gone over it. I have not started either this month, so going.
We'll
I've already done
run through the
exams really good.
If you'd like to leave, I mean, you could have left this entire time. I'll give you official permission to leave now. Good luck on the noise.
Yeah, I'm just curious. It's really look through.
The error.
I also looked low key, I think the second two tests are way better.
Let's just go through winter 2025.
The second one.
The one that I did.
You don't get to know questions.
And the second two are really
Okay. So, essentially, these are some long paragraphs, but recent events regarding deportations have raised scrutiny about the impact of immigration, receiving immigrants. Blah, blah, blah. We want to express the causal relationship between the number of immigrants on the natural log of local GDP per capita using this model. Here's the possibilities regarding the relationship between y and x1i. Which, if any, of the possibilities are a reason why beta 1 might be negative. Okay. The answer to this one is E. Because immigration increases the size of the labor supply without a proportional increase in labor demand, lowers wages, increases unemployment, decreases productivity of the labor force. Right? So more immigration, lower log GDP. Right? That's why the answer is E right here. Okay? Which is a possibility why beta 1 might be positive. The answer to that would be C. More immigration means increasing economic activity. Okay? That's going to be a positive. Which, if any, are a reason why beta 1 might be 0? That would be B. The arrival of immigrants induces an equal number of native-born workers to move away, leaving economic activity unchanged. So immigration means that economic activity is unchanged, beta 1 of 0. Okay. The rest of these are not included in the Econ answers. Any questions about that?
Can you zoom in a little bit?
Yes, that's great. Okay. Using the sample stats above, calculate the bivariate OLS estimates. You guys did this in exam 1. So you just know the covariance, and beta naught is y bar minus beta 1 x bar. That's how you solve for. Thank you.
Thank you.
Yeah. See you guys. Good luck. You have a formula for the predicted value, so you're going to use your estimates and you're going to predict the value just like you did in exam 1. Number 6, compute the residual. Again, you did that in exam 1. State the critical assumption, exogeneity. This is all going to be familiar for a while, right? Number 8, 3 reasons why the critical assumption might be violated. Reverse causality, simultaneity, omitted variables bias, measurement error. Those are all reasons why exogeneity could be violated.
Is reverse causality and simultaneity the same?
They're very.
My understanding they are, but maybe.
Yeah, they're so related that they might not count as 2 different answers, honestly.
Okay.
They're technically different things, so. Yeah. What sign would you expect alpha 1 to have? That's just using your intuition. Number 10, derive an expression for covariance of x1 and epsilon in this case, right? That is the omitted variables bias derivation, which you guys also did on exam 1. Okay? Number 11, from your answer, under what condition would OLS be unbiased? It's if you have a coefficient on there, you end up with alpha 1 times some fraction. So if alpha 1 was 0, then OLS could still be unbiased, right? Okay, perfect. Number 12, what 2 conditions have to be true for, okay, now we get to IVs, now we get to new stuff, okay? What conditions? Exogeneity and relevance, right? We wrote those out mathematically and described them as well. 13, this is a happy face, sad face question. Okay, so discuss the validity of the 3 candidate instruments. So he's got whether the city has a thriving tech startup scene, or SEN, the last 3 digits of the mayor of the city's social security number, and the existence of cultural enclaves from various ethnicities because of historical settlement patterns. Okay? So, predictably, probably you're gonna have, a happy face and a sad face for the first one, maybe a sad face and a happy face for the second one, and 2 happy faces for the third one, because the third one actually makes sense, right? So you can do your relevance exclusion chart just like you did in class, and as long as you can explain your reasoning there, then you're good. Okay. Number 14, you flip a 3-sided coin and pick one of the 3 candidate instruments to be your instrument. Okay, so on number 14, let's see, what's your bivariate IV estimate? We already did that. It's the covariance of z and y over the covariance of z and x. Prove it's consistent. We did the consistency proof. All right. You're a little unsure about your assumption, and you'd like to test the assumption. Okay, true or false? Using data from your data set, it is possible to test the assumption that the covariance between z and epsilon is 0. What do you guys think?
Well, you need to be over-identified in order to do any test, right?
I go to Stata, covariance z epsilon, see what it spits out. No, right? By construction, the covariance between z and your residuals is going to be 0. That's how OLS works. That's not a way to test exogeneity, right? So using data on just y, x, and z, you cannot test that assumption. In order to test this, you need to obtain additional instrumental variables so that you're over-identified. What you guys just said. Okay. Reasons to obtain additional instruments, E and F, we talked about that one. What's the name of the IV estimation procedure you use when you have more excluded instruments than endogenous x variables? That's 2 stage least squares. Give a formula or describe in detail how to obtain the estimate. We did that one on the board. That was the 2 stage least squares example. Okay, then he asked you to do a Hausman test. We did the Hausman test, or we got through it. Okay, although you're fairly proud of your IVs, you decide to be extra sure and collect time series data going back many years. Okay, so we're going to do that. We're going to collect time series data. Denote your observations of log GDP over time of YT and integration rate over time of XT. Graph your data over time, and you find log GDP per capita and integration have been steadily increasing over the years. What problem is this likely to cause for a regression? Yes, you're going to get a spurious regression, which is essentially omitted variables bias. Those are pretty much the same thing because you have trending data. Okay. The solution to this problem, you could include a t. That's great. Or you could detrend by partial regression. That's Frisch-Waugh that we talked about. Okay, number 24. Suppose you wanted to investigate how changes in immigration in 1 year affect the economy over several years. This is kind of an awkwardly worded question, I think. Specify a regression equation that would allow you to estimate how the effect of immigration evolves over time. What he's looking for here is FDL, right? So you just write out an FDL model, boom, that answers that question. Okay, in time series data, where unobserved factors often persist, which Gauss-Markov assumption is violated? No serial correlation, right? That is violated, and in that case,
sorry, is that 8-2?
It's A3.
Oh,
But you should write the assumption. You should write.
My board actually is, yeah.
For the assumption you identified in the previous question, give the consequences for OLS if it's violated. What are the consequences for OLS?
Biased, inconsistent.
It's not.
Inefficient.
Yeah, it's inefficient. Your standard errors are wrong. Okay? And so since your standard errors are wrong, you can fix your standard errors with Nui West. Yep, you're going to use Nui West for that one. Okay, take your OLS results, put together a PowerPoint, the mayor's convention, they like your plaid transitions, animations.
Your results.
But not your results, okay? So, then you go and collect panel data over several years. You come back. Of what sign is the likely correlation between alpha I and X1 IT? Again, this is just like your intuition. If alpha I and XIT are in fact correlated, is OLS biased or unbiased? It's biased, right? This is the sussy alpha problem that we were talking about.
For questions like 27, if we just give a good enough explanation, are you good with either way?
Yeah, I mean, alpha I is this is the individual, and then X1 IT I think was your.
That's immigration, right?
Immigration for a city in a specific period.
So we put immigration impact, would that be enough?
And then you have a piece that captures innate proneness for, into a piece that captures innate proneness for economic thriving, okay? So what I said was it's probably positive because if you have a proneness for economic thriving, then that probably increases immigration and vice versa. Right. So that's what I said for that one. Describe two consistent estimators in this case to fix the sussy alpha problem. Okay? And we talked about that. That's first difference thing and fixed effects. Okay? Then examining your panel data, you get this diff and diff, right? But like if you see something like this, that just screams diff and diff. Okay? So just write that. Your estimation strategy. Using the estimation strategy identified what's the effects. We talked about measuring that effect. Like you can do it just by looking at these numbers right here. What's the key assumption? It's parallel trends. If the assumption were true, what would log GDP per capita have been in 1980 for Miami if Miami had not experienced that large influx of immigrants? So, I mean, it's 8.2. Minus 0.2 would have been 8.1, right? So then give a regression model that could be used to obtain the estimate you calculated. And now you're going to use, this isn't asking for generalized, this is just the 2-period, 2 individual diff and diff, right? Treated after, that's wrong. So that's what you would write right there. Okay, as the last arrow in your quiver, you analyze the effects of immigration on occurrence of a local recession. New outcome variable equal to 1 if the city had a local recession and 0 otherwise. You have a reason why OLS may not be the best way to estimate the effects on this new binary outcome. What do you guys think?
Go out of bounds.
Yeah, we go out of bounds, right? OLS is linear, so your LPM model could give you probability below 0 or above 1. So that's not what you want. So instead of a linear model, you estimate this, where G of something is a link function. So what characteristics should a suitable link function have?
Increasing and within bounds.
It should be monotonically increasing and provide values between 0 and 1. Yes. Give either the Probit or Logit link function. You can give either one.
Can we just write like the I with the circle, whatever it's called?
You could if you said where that is the standard normal CDF. That would be sufficient.
And the other one's just EW over 1 plus EW, and that's all you need.
E2 though.
Yeah, EW.
E to the W.
Yeah, E to the W. Sorry. Okay, and then we also defined the likelihood function. I wrote that on the board. And then the marginal effect, I also wrote that on the board. And that is the whole final exam from.
Yes.
It's not bad.
You did so
I can get a
well,
50 on it.
guys.
Okay. Any last questions?